Hello everyone. Nuclei Part 1: Atomic masses, composition, size of nucleus, binding energy, and nuclear force. These are the topics that will be discussed in this video. So first we can see about the atomic mass and composition of nucleus. We know that the mass of an atom is concentrated in the nucleus. Since the mass of an atom is very small, we have to use a different unit, that is atomic mass unit. And one atomic mass unit is defined as 1 by 12th of the mass of 12C carbon atom. And in kilogram, its equivalent value is 1.660539 into 10 raised to negative 27. Now the mass of an atom can be accurately measured using a mass spectrometer. Now atoms were found to have the different atomic masses but the same atomic number. And these atoms are called isotopes. And each element is a mixture of these isotopes. Now hydrogen has got 3 isotopes and they have got masses 1.0078 units, 2.041 unit and 3.0160 unit. The nucleus of the lightest hydrogen atom having a relative abundance of 99.985% is called proton, while the hydrogen having mass of 2.041 unit is known as deuterium, and the hydrogen atom having mass of 3.0160 unit is a highly unstable element and is not freely found in nature. It can only be prepared under laboratory conditions. Now the proton is a positively charged particle in the nucleus, and the negatively charged electrons are present outside the nucleus. This is according to the quantum theory. Now the total positive and negative charge of an atom has to be equal since the atom is electrically neutral. And these charges are positive Ze and negative Ze, where Z is the atomic number, which is equal to the number of electrons. Now the presence of isotopes meant that there was some neutral particle inside the nucleus, which was the reason for the different atomic masses. And the presence of neutral particles were discovered by James Chadwick in 1932 by the observation of neutral radiation emitted when a beryllium nuclei were bombarded with alpha particles. Now the neutral particles which James Chadwick discovered were named neutrons. Free neutrons are unstable compared to free protons. That is, it decays into a proton, an electron, and a antineutrino and has a mean lifetime of 1000 seconds. Now we can see the formula A is equal to Z plus N, where A is the mass number, Z is the atomic number, and N is equal to neutron number. Now the neutrons and protons are called nucleons, and the total number of nucleons in an atom is equal to its mass number. Isobars are nucleides with same mass number A, and examples are hydrogen 1,3 and helium 2,3. Now isotones are nucleides with same number of neutrons but different atomic numbers. Example Hg80 and Au79 Now size of the nucleus. Scattering experiments with fast electrons as projectiles that bombard targets made up of various elements can be used to accurately measure the sizes of nuclei of these elements. It has been found that a nucleus of mass number A has a radius r is equal to r0 into a raised to 1 by 3, where r0 is a value which is equal to 1.2 into 10 raised to negative 15 meter. Hence, volume of an atom is proportional to mass number. The density of nuclear matter is a very large number, and it is approximately equal to 2.3 into 10 raised to 17 kilogram per meter cube. Now we can see the relation between mass and energy. It was Einstein who showed from his theory of special relativity that it is necessary to treat mass as another form of energy. And Einstein gave the mass energy equivalence relation, which is E is equal to mc square, where E is the energy and m is the equivalent mass and c is the velocity of light in vacuum, which is approximately equal to 3 into 10 raised to 8 meter per second. Now, experimental verification of the Einstein's mass-energy relation has been achieved in the study of nuclear reactions amongst nucleons, nuclei, electrons, and other more recently discovered particles. In a reaction, we can use the conservation of energy law, which states that the initial energy and the final energy are equal, provided the energy associated with mass is also included. This concept is important in understanding nuclear masses and the interaction of nuclei with one another. Now we can see the concept of nuclear binding energy. First, we can see what we mean by mass defect. That is, the nucleus is made up of protons and neutrons. So logically, the mass of the nucleus is equal to the sum of the mass of protons and neutrons. But in reality, it is not like that. The nuclear mass is always lesser than this sum, and this is known as mass defect. And mass defect delta M is equal to ZMP plus A minus ZMN minus M. And in this case, ZMP plus A minus Z into Mn is the mass that we get logically, and capital M is the actual mass. Now, to understand mass defect, we have to use Einstein's equivalence of mass and energy. Since the mass of the nucleus is less than the sum of the masses of its constituents, the equivalent energy of the nucleus is less than that of sum of the equivalent energies of its constituents. That is, if a certain number of neutrons and protons are brought together to form a nucleus of a certain charge and mass, an energy EB, which is called the binding energy, will be released in the process. And binding energy is the energy required to separate the nucleus into its constituent nucleons. Now, this is a graph showing binding energy per nucleon and mass number A. Now, binding energy per nucleon, EBN, can be calculated as EB by A, where A is the mass number. From this graph, we can make the following observations. That is, the binding energy per nucleon, EBN, is constant. That is independent of atomic number for nuclei of middle mass number, that is between 30 and 170. Now, EBN is lower for both light nuclei, that is for lesser than 30, and for heavy nuclei, that is for A greater than 170. So, several conclusions can be drawn from the two observations. First is, the force is attractive in nature and very strong, producing a binding energy of around a few mega electron volt per nucleon. Now, the second conclusion is, the constancy of the binding energy in the range of 30 lesser than 170 is a consequence of the fact that the nuclear force is short-ranged, and the property that a given nucleon influences only nucleons close to it is also referred to as the saturation property of the nuclear force. This is the reason for this phenomenon. Now, for a very heavy nucleus, say A is equal to 240, it has got lower binding energy per nucleon compared to that of a nucleus with A is equal to 120. Thus, if a nucleus A is equal to 240 breaks into two A is equal to 120 nuclei, nucleons get more tightly bound. This implies energy would be released in the process. It has very important implications for energy production through fission. Now, for very light nuclei, if they join to form a heavier nucleus, the binding energy per nucleon of the fused heavier nuclei is more than the binding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. Again, energy will be released in such a process of fusion. Now we can see about nuclear force. Nuclear force is a strong attractive force which holds the protons and neutrons in a tiny nuclear volume, or the force which holds the nucleus together. Now, many features of this force have been found out through experiments carried out from 1930 to 1950. Now, we can see some of the features of this force. One is the nuclear force is much stronger than the Coulomb force acting between charges or the gravitational forces between masses. Then second is the nuclear force between two nucleons fall rapidly to zero as their distance is more than a few femtometers. This leads to saturation of forces in a medium or a large-sized nucleus, which is a reason for the constancy of binding energy per nucleus. Now the third feature is the nuclear force between neutron-neutron, proton-neutron and proton-proton is approximately the same. That is, they are independent of the electric charge. So this is the end of this video. In this video, I have discussed about atomic mass, the size of nucleus, binding energy, and nuclear force. If you have got any doubt, please comment in the section below. Thank you.